Afternoon, everyone. Myself, Bhavana Anchan, and I'm a PhD scholar in the Department of Atomic and Molecular Physics in MAHE, Manipal. I work under Dr. Suresh D. Kulkarni and Dr. Ajit Kumar Patil. So, presently, my today's talk is on vitamin B detection in aqueous medium using MPA-CdTe quantum dot. So, these are the outline of my presentation today. And what we all know is we only speak about vitamin in terms of supplements. So let's get into vitamin. What exactly a vitamin uh, like it is. So to start with, vitamins is a organic compounds which is normally essential for our normal health and well-being. And we know it is found in trace amount in our body, and to have that we have to have a good dietary like good food which has certain vitamins and minerals, whatever it is. So our main focus of interest is in vitamin B12, which is called cobalamin. So it is a water soluble vitamin, and it plays a vital role in many of the mechanism, as well as in the formation of red blood cells and many extra synthesis processes. And in few cases, many of the cases, the deficiency has, as well as the excess of these vitamins, can result to lot of complications. Okay. So the levels which is required by us in day-to-day life is in the like almost around 0.4 to 2.4 microgram per day, ranging from adult infants to adults. And in serum, the levels of vitamin B12 is around in 200 to 900 picogram per ml. So it is very, very small. So, that therefore they always say that it is caffeine for the cells. Okay, that is, it keeps us active, like how coffee keeps us active. Same way, this vitamin B12 is very essential because it is related to a certain mechanism which is indirectly to neurological related issues. So it if there is a reduction in the value of in the vitamin B12, it results to certain neurological problems such as Parkinson, Alzheimer, peripheral neuropathy, and etc. So vitamin B12 is essential. So let's look into deeper into the architecture of vitamin B12. So if you look into the figure, it has a chlorine ring where cobalt is at the center, and fifth nitrogen is connected to one more group at the bottom, and then there is a sixth group which has a ligand can be attached. So based on the variations of the ligands, the names changes. Okay, it can be methyl globulin or hydroxy cobalamin, so etc. And then detection challenges. So as we already know that it is found in a very trace amount, and there are very many methods which can detect vitamin B12. So in like mass spectroscopy, HPLC, as well as ELISA, and what happens is these methods are very, very complex in few cases, and it is very costly and time consuming. If you consider ELISA as an example, which is basically used in hospitals, it takes minimum 3 to 5 hours to get you the results out of the this one, because it has continuous washing process, incubation, many other processes. And also you need a trained person to actually to do the experiments detection. Therefore, there is a need for this simple technique which can actually sense this vitamin B12 molecule. So there are various studies which actually showed the interaction of detection of these vitamins. So basically by utilizing these fluorescence or organic compounds through various methods, as well as spectroscopy method. So here in our case, we are actually looking into um, um, material which can actually help us to enhance the sensing, as well as help us to go to that level of sensing where we can detect vitamin B12 in the serum. So to start with, we have started with synthesis of quantum dots. So here I've used CDT quantum dots. So what I have done is I've taken cadmium chloride along with the MPA, which is a capping agent. I've used MPA because cadmium has a tendency to undergo oxidation in the solution. So MPA actually shields this cadmium so that it does not undergo oxidation and be soluble, water soluble. Okay. So in the presence of potassium telluride, basically this is a one-pot synthesis method. Okay, so it is put in a beaker, all these chemicals, and then it is stirred continuously, and the mixture of sodium borohydride and citric acid is added to this, and then it forms a cadmium seed particles. And later it will have a color, it will be like brown precipitate because it has a seed particles within that. And also due to the presence of MPA as well as citric acid, the pH of the solution is acidic. So now I have to reduce it below pH 7. So what will I do is I'll add sodium hydroxide to that and then change the pH of the solution. By varying the pH of the solution, I can actually tune the size of the quantum dot. So I have started varying from 8 to 12 pH, and I've got various sizes. I have tuned the sizes of the quantum dot. So, and then, yeah. So this is about the synthesis. And then here you can see I've given the 5 different quantum dots, which is actually for different sizes. And you can see the corresponding absorption and the emission peaks of these quantum dots. And the ranges of this size was around 2.7 to around 6.9 nanometer in range. And in the figure 5, you can see the TEM image of one of the quantum dot, which size is around 4.27 nanometer. And from the FTIR plot, we could see that the SH bond, which is around at 2500 centimeter inverse, which is actually vanished in the, to say that there is a bonding of MPA happening onto the cadmium, forming the MPA capping onto the CDT quantum dot. And further, once the quantum dot was synthesized, I tried to understand what is the spectroscopic interaction between this quantum dot and the vitamin B12. So I have taken one of the size of the quantum dot, that is around 4.27 nanometer, and which has an absorption around 520 nanometer and emission around 558 nanometer. When it is excited at around 275 nanometer, it gives a maximum fluorescence. Maximum fluorescence. Okay, and then in the figure 7, you can see the excitation peak of the CDT quantum dot, emission and absorption. Yeah, and then it's like to start with, initially you have to know what is the concentration of quantum dot you're using for your experiment. It's like randomly we can't take any quantum concentration because there are various parameters which affects our experiment. So initially, like taking a higher concentration can lead to, you know, there can be reabsorption happening, there can be self-quenching happening or aggregation happening. So a particular concentration is essential to start with the interaction. And so I have optimized the concentration of quantum dot. So here I have varied the concentration from 5 nanomolar to 110 5 nanogram per ml to 110 nanogram per ml. And you can see in the figure 8 that there is an increase in the this one values, and then after 15 nanogram per ml there is some variation happening, and then it is stable. So it is like there's a self-quenching happening within after certain concentration. So here what I have done is I have actually fixed the concentration for around 15 nanogram per ml. So that is a concentration which I've used for my interaction studies. Okay, and then once the concentration is set, initially I should know what is the absorption absorption of the vitamin B12. So if you see into the figure, you can see it has a maximum absorption at around 361 nanometer, as well as there is a broad branching, shoulder peak around 510 to 540 nanometer. Okay. And this 510 to 540 nanometer basically give the color to the cobalamin. Okay, so if what you get vitamin B12 is around maroonish red in color. So that is basically due to that. And so before starting the further fluorescence quenching related experiment, the absorption spectra was taken for the fixed concentration of quantum dot, varying the vitamin B12 to see whether there is a ground state complex formation happening. Okay, so but from the results we have found that there is no new peak which was there, and therefore we can just reject the possibility of ground state complex. Yeah. And then the fluorescence studies were made where the concentration of VP12 was varied from 300 nanogram per ml to 10 nanogram per ml. And then the Stern-Wilmer plot was plotted, which shows a linear trend. And the limit of detection is around 0.3 to 6 nanogram per ml. And the limit of quantification is 1.22 nanogram per ml. Okay, and the further, if you look into the comparison, you can see overall it is much better than other techniques or other limit of detection. And further, the studies were also done for interaction studies to see how these other ions or interacting molecules result in the fluorescence, as well as it was tested for the serum studies, where we could see there is a very, like, we could actually sense what is the levels of vitamin B12. Okay, yeah. So there is furthermore experiments to be carried out for various excitation, because all these was done for a particular excitation of 361 nanometer, thinking that it is the absorption peak is maximum at 361. But there is a branched peak, shoulder peak, which is around 510 and 540, which comes closer to our emission of quantum dot. So there is a high tendency that there is an energy transfer from the vitamin B12 to the quantum dot. So that further experiments is there, but I'm not included into this paper. So here I've only discussed about 361 peak. Okay, so this, and yeah, so this is the references I've used, and these are the studies I've done, like patents and papers.